Hi everyone, this is Ken 422, week number 5, and this week we'll be just doing an exam review in preparation for your test, which is next week on September 29th. So there's an exam 1 review. Homework will be due on September 22nd at midnight, so the date of this lecture. And then I'm assigning another homework number 5, which is basically a review set, to prepare for your test. Exam 1 is scheduled next week on September 29th during your scheduled lecture time. So it will be from 2 p.m. to 4:30 p.m. next Tuesday. The exam will cover topics covered in weeks 1 to 4. So specifically, we're looking at kinetics of homogeneous reactions, IBR kinetics, introduction to reactor design and ideal reactors, and reactor size comparison. So basically, just make sure to study the slides posted over the past 4 weeks. Just some rules about the exam. I'll send these in a separate email as well early next week, just to remind you. So the exam will be made available under the exam 1 folder. Under exam 1 in the week number 6 folder in the course materials on the day of your exam. Myself and the course GA will be checking students in from 1:45 p.m. on September 29th. So make sure to show up early. You cannot start your test unless you check in with me first. You're expected to have a laptop camera, phone, whatever electronic device that has a camera. Your camera must be switched on during the exam duration, so I have to be seeing you during the entire exam duration. The exam has to be taken in one sitting, and you make sure to save your answer as you progress to avoid, having any technical issues with Blackboard or any other tool you're using. You have 20 minutes after the test or the time of your completion, whichever is earlier. So if you finish your exam in 30 minutes, you have 20 minutes after the time you turn it in to upload all your work to Blackboard, or email it to me if you're having some difficulty. Upload whatever work you want to be considered for grading, okay? So you only have 20 minutes, so just please stick to the time requirements for the test. Exam is open notes, open book. However, lecture videos cannot be played during the test. Exam time is limited, so I recommend you prepare your own formula sheet, or if you have the slides, maybe write some notes on a sheet on the side so that you can avoid studying during the test, right? If you start studying during the test, now you're wasting a lot of time. If you have any immediate issues, or if you have immediate issues with any of the information in this announcement, please contact me. We'll work towards addressing them, but please get in touch with me a few days before the test. And if you need any special accommodations, please contact me as soon as possible. And again, unexcused absence will count as a 0. If you have an excused absence, please let me know 48 hours in advance so that I can, prepare for it. Okay, so talking about the test, your test will consist of 10 multiple choice questions, 2 points each. Multiple choice questions will be completed on Blackboard, and then you're going to have 4 problems to be solved. Each problem is worth 20 points. When solving these problems, you're going to have a box on Blackboard to enter your final solution, and then you're going to upload your entire work to Blackboard within 20 minutes after your completion time. Okay. 80% of the test will be taken from your homework. So just if you study your homework, you should have no issues getting an 80%. Very likely much more than 80% will be taken from your homework. You will need a calculator, so please bring your calculator. Bring a good calculator you're familiar with. Don't just be prepared and prepare yourself to be time constrained. The exam will fit the 2-hour time to which it's allocated to, so please plan for that. And this is the Zoom link for your exam. So just be careful for that. I will also send an announcement on the day of the exam or the day before, reminding you of the Zoom link and all of these other rules. Okay, finally, just a final set of rules for you. There will be multiple versions of the test. Each person will have a completely different test, basically. Considering all the iterations, so you're either going to have a different number, maybe different questions, whatever it is. You're not authorized to post this exam online or share it anywhere. Please be careful of this. The exams are designed in a way that whoever shares it, because every test is unique, basically, and attempts at any funny business will result in a 0. Okay, so let's avoid these issues. Let's just study for a test, do your best, work hard, and you're gonna get there. It will be fine. Okay, so let's start the review. So going back to week number 1, the first point you need to remember is what is a rate of reaction, and basically the units really is what I'm looking for. And again, the rate of reaction is usually change in number of moles with time, dNi by dt, multiplied by some other parameter, either a volume, mass of solid, interfacial area, whatever it is. And this is really your rate of reaction. The most common units for rate of reaction is moles per volume per time. So just be aware of this. The second thing you need to know from week number 1 is the units for the reaction rate constant, which is the K basically. So the units are time to the -1 multiplied by concentration to the 1 minus n, alternatively 1 over time multiplied by concentration to the n-1. These are the units of the K parameter. And this is the second thing you need to know from week number 1. Okay, third thing is molecularity. It's not very important, but just be aware of these basic chemistry definitions. And this equation is very important. This is going to show up, I'm telling you, so be prepared to use this equation. Consider if you have a reaction at 2 different temperatures and the activation energy does not change with temperature, then the ratio of the reaction rates is equal to E over R, 1 over T1 minus 1 over T2. A few things to remember about this sort of equation is that, first of all, if you're using R, 8.31 joule per mole Kelvin, you can use any set of units you want, but if you're using a standard unit, just note this down. One thing to note is that this is in joules. Activation energy is usually reported in kilojoules, so you'll need to multiply it by 10 to the 3 joules, okay? So this is a basic conversion you tend to forget, or it's a common error when solving these types of problems. The temperatures have to be in absolute units, right? So absolute units means Kelvin or ranking. So in our case, we're using Kelvin. Degrees Celsius will not work. So just be careful of this. And again, to convert from Celsius to Kelvin, degrees Celsius plus 273.15, if you want to be fancy, is equal to Kelvin, okay? So just note these things when using this equation. Okay, and then this is a typical example. I think this problem is in the homework. So, this type of thing is going to show up, this similar example is going to show up on your test. Okay. After that, so this is basically what you need to know from week number 1. From week number 2, if you remember, we're talking about interpretation of batch reactor data. We talked about the integral method. We talked about the differential method. We're in this course, we're focusing on the integral method, sorry. And we said we're going to cover a bunch of cases. And you need to know 4 cases for this test, or you should focus on 4 cases for this test. First one is when you have an irreversible unimolecular first order reaction. So it's A goes to products with a reaction rate constant of K. In this case, minus RA is dCA by dt is equal to KCA, or minus dCA over CA is equal to KDT. If you do some manipulations, this is the performance equation which you need to know, okay? So be prepared to use this equation for an irreversible unimolecular first order reaction. Alternatively, Ca is equal to Ca naught exponential minus Kt. Be prepared to also use this equation as well. We also introduced the concept of conversion, so you should be able to should understand what conversion is and be able to use it when solving problems. And again, Xa is equal to 1 over Ca minus Ca naught, right? So different forms of Xa, 1 minus Ca over Ca naught, or Xa is equal to Ca naught minus Ca over Ca naught. Ca is equal to Ca naught into 1 minus Xa. All of these, basically these three equations, you should be able to use them interchangeably, especially when deriving a performance equation or something like that. Okay, so again, for a reversible first order reaction, this is the performance equation for this case. So you need to be familiar with this and know when to use it. Okay. Second case you need to know is an irreversible bimolecular second order reaction. So this is when I have A plus B goes to product, so the reaction rate of K. And again, you can read this at your own time or revise it at your own time and come to office hours. But basically what you need to know from this case, derivation, all this stuff, you're not going to get asked to derive any of these equations. You can, it's good to know, it helps you understand the physics, but for our case, I'm only interested in the performance equations, right? Which is really what you're going to use to solve problems. So this is the performance equation for when I have two different species. And again, recall that M is equal to Cb naught over Ca naught. Okay, so here M, where's the, there it is. M is equal to Cb naught over Ca naught. And this is the case when I have bimolecular case, bimolecular second order reaction. Bimolecular, okay? And you need to be able to use this performance equation to solve problems. And you also should know that this equation is not valid when M equals 1. You're going to have, it's mathematically incorrect. So when you have M equals 1, so in the case when it's 2A equals to products, or 2A goes to products, this is the performance equation you need to use for a second order reaction. So again, for an irreversible second order reaction, if it's bimolecular basically means A plus B goes to R. This is the performance equation. If it's unimolecular, basically 2A goes to R or goes to products. This is the performance equation for a second order reaction. Okay. And then the final case, is this the final case or the third case? Yeah, so if you assume this is the second case, this is the third case you need to know. So basically the fourth case will be for an nth order reaction, so it's more of a generalized term. You can see that R is equal to K Ca to the N. I don't know what N is. And again, minus dc, if you rearrange this, you get minus, basically separating the variables. I'm moving this Ca to the bottom, moving this dt up here. I get this equation, which then I can integrate to get my performance equation for this scenario. And this is not valid for n equals 1. Very important to remember. This equation not valid for n equals 1. Okay, you cannot just plug in 1 here and use this equation. If n equals 1, if it's a first order reaction, go look at case number 1. Okay, and when these types of problems, you need to be prepared to do some trial and error or some iteration to get the value of n, and we're going to have a look when solving the homework later on. So this is the fourth case, and again, for a zero order reaction, this is the equation. Yeah, so just be aware of case number 4. Okay. This is another equation, just, this is really simple, but just be prepared, this might come. I don't think it's going to come, but just understand the concept of half-life. Half-life is the time when the concentration drops to the half of the initial concentration, and just be aware of it. You know, it might come in a multiple choice question or something. Okay, then we move on to week number 3, where we introduced the 3 types of reactors. We said you have an ideal batch reactor, plug flow reactor, continuously stirred tank reactor, and you know, they're all very different. Batch reactor, I load chemicals into a vessel, I mix it, leave it, and then after some time, I just take the product out. And this is non-continuous. And here I assume it's perfectly mixed. So a couple of things to know. This is not continuous. There is no continuous flow. And perfectly mixed, right? These are really the 2 things you need to know. A PFR, I have feed going into a tube, and I get products on the other end. And here we assume that, you know, they're like, you know, plugs pushing each other. And here there is no mixing, and it is continuous. These are the 2 main properties besides, you know, its operational, you know, properties. And finally, CSTR, I have feed going into a vessel. Vessel is full with with a volume, constant volume, usually at steady state. And I get products being taken out, and I'm continuously mixing. And, you know, here this is perfectly mixed as well. And it's continuous, okay? So by continuous means I always have flow going in, coming out, constant flow, whereas in this one I don't have flow going in and coming out. I charge it at t equals 0, and then at t equals t end, I just take the products for a batch reactor, okay? So understand the 3 types of reactors, understand the differences between them. This is really the core of this course. So it's very important that you know this. And this is the slide with the differences, or, you know, with the properties. So read it, make sure you know what these are. Okay. Then we need to know the performance equations of the 3 types of reactors and be able to apply them. So performance equation for an ideal batch reactor, this is the performance equation. You know, RA is your reaction rate, whatever it is. So it's first order is KCA, second order KCA squared, KCA to the power n, whatever it is. Substitute in the performance equation, do your integral, solve the problem. The performance equation for a CSTR is basically this. So be able to, or, you know, this is the general performance equation up here. V over FA naught is equal to tau over CA naught is equal to XA over minus RA. And then you plug in the equation for minus RA, whatever it is, if it's KCA, KCA squared, whatever it is. And here the volume is in meter cubed. This is volume. This is your molar flow rate. It's in mole per time. This is your space time, which is in seconds. This is the concentration in mole per meter cubed. And of course, this is the conversion right here. So, you know, just be able to use all of these different units. Again, for a first order reversible reaction, you can directly use this performance equation as well. Okay, so moving up here to the concept of space-time and space velocity, you should also know these equations. So this space-time, and space-time is the time to process 1 reactor volume of feed. The units of this is seconds. This is your volume right here. And this is your volumetric flow rate. So this is in meter cubed per time or liter per time, whatever it is. This is your volumetric flow rate right here. This is your volume, concentration, molar flow rate, volume as well. So just be comfortable with the concept of space-time, because it shows up in week number 4 when we're, you know, having reactors in series and all this stuff. Okay, performance equation of a CSTR, know how to use it, practice the homework, practice how we, you know, substituted. Really the main skill is just plugging in your reaction rate minus RA here and solving this equation. This is really the main skill, whether it's in the CSTR, the PFR, or the IBR performance equation. Okay, finally, your plug flow reactor. Just understand that the plug flow reactor is a cylinder. We assume that it's composed of smaller plugs or smaller cylinders, all of them are pushing each other. There is no mixing in the direction of flow or in the axial direction, basically. So there's no mixing in any of these directions. And this is the PFR performance equation. And again, you should be able to use it. And primarily the main point of this performance equation is that, you know, dxa over minus RA, if I give you a reaction rate, you just rewrite it in terms of X and you do this integral. If I give you a reaction rate and you don't want to, you just want to solve in terms of concentration, you write it here and you do this integral right here. You get your final expression, you solve for whatever parameter you're being asked for. Okay. And then you need to know, if it might come as a multiple choice question, why are the performance equations for the IBR and PFR so similar, right? If you recall the performance equation for PFR, we said it's tau is equal to CA naught integral dxa over minus RA. This is for a PFR, whereas for an IBR, the performance equation is T is equal to CA naught integral dxa over minus RA. You can see that they are very similar, almost identical. And why are they very similar? It's because, you know, you can assume that a PFR is just a bunch of small IBRs just pushing each other or plugging along. And that's why it ends up with both of these equations being almost identical. So just, you know, study the slide, get an idea in case it comes as a multiple choice question. Okay. So now let's move on to week number 4 when we were doing size comparisons for single reactors. And again, we said for n not equals to 1, if I just rearrange the performance equation for a CSTR and rearrange the performance equation for a PFR to get this parameter, tau k Ca naught, I'm going to get this expression. And just remember that the parameter tau k, right, tau k is a dimensionless parameter, which you can use to compare volumes, right? Which can be used to compare volumes. So just be aware of this. If you want to compare any two volumes of any two types of reactors, or, you know, you want to compare the volume of the first CSTR to the second CSTR, you need to use this parameter tau k to compare the volumes. Or, you know, the most common trick is to use this parameter to compare the volumes. Okay, and, you know, this, if this shows up, it's going to show up on a multiple choice question, where basically you need to understand that if I compare the performance of a single mixed flow and a plug flow reactor, so here I'm comparing the volume of a mixed flow reactor or a CSTR to the volume of a PFR for different reaction orders. So I have n equals 1, n equals 2, n equals 3. These are the lines, and here it's 1 minus XA. And, you know, you can see from this chart, we can make a bunch of conclusions, you know, that the volume of the CSTR is always larger than the volume of a plug flow reactor. So I always need a larger CSTR to achieve the same conversion as in a PFR, basically. So if I have a PFR and I have a conversion of 90%, so 1 minus XA is 0.1. And I look here, it seems that I will always need a larger CSTR to achieve the same conversion. So basically, in terms of volume, in terms of space, a PFR is much more efficient than a CSTR. This is really the idea we're trying to convey here. And this is just a, you know, comparison of the 2 points. You can read the slides for week number 4. And then you should also be aware of the idea that if I have equal number of so here I'm comparing the volume of n CSTRs versus 1 PFR, right? N CSTRs versus 1 PFR. So is it better to just number of CSTRs versus 1 PFR? And the idea here is you need to think, if I'm comparing basically the volume of CSTRs, am I better off increasing the number of, or basically keeping the number of or am I better off just using a larger CSTR versus using multiple CSTRs in series? This is what I'm trying to say here. So here, if I move along this line, I'm using basically one CSTR, but it's just, getting bigger, right? Increasing the volume. So if I have one CSTR and I keep on increasing the volume, I can, I will never be able to reach the performance of a PFR, basically. So if you look here, if I'm looking for a conversion of 90%, so if I'm looking at a conversion of 90% here, I will need a CSTR which is 10 times the volume of the PFR, right? So XAF is equal to 0.9, 1 minus XAF is equal to 0.1. Read it off this chart here. I'll go look at actually not this point. I look at this point basically for one CSTR, and I find out that's equal to 9. So I need 9 CSTR which is 9 times as large. If I need a conversion which is 0.98, I'll need a CSTR which is almost 50 times as large. And if I need a CSTR, or if I need a conversion of 0.99, which is, I need a very high conversion, you'll see I need a CSTR which is almost 100 times the size of the PFR, okay? And these dashed lines are tau k, so these are basically the volume of a CSTR, okay? Alternatively, what we're trying to introduce is the idea that instead of using one CSTR and just making it bigger to try to achieve a higher conversion, you can just put CSTRs in series, okay? So if I look at the dots here, so for one CSTR, I'll need the tau, the ratio of volumes will be 9 to achieve a conversion of 0.9, right? So I can just keep the same total volume. So I can keep the same total volume of 9 and just increase the number of CSTRs. So instead of using a larger CSTR, I can just use 2 smaller CSTR. This is with the same total volume. So if I move from the blue dot to the red dot, the difference between the blue dot and the red dot is that this is just one large CSTR with a tau k equals 9. This point corresponds to 2 smaller CSTRs with an overall tau k, tau k total is equal to 9. So maybe this 4.5, this 4.5, maybe this 3, this is 6, whatever it is. Just there are 2 CSTRs in series, and I can achieve a higher conversion while keeping the same overall volume, right? So if I have 2 CSTRs here, n equals 2, and XAF is 0.97, or 1 minus XAF is 0.03, so XAF is equal to 0.97. Additionally, if I just increase the number of CSTRs to 4, so here at the green point, I have 4 CSTRs, you can just draw them, whatever it is. And the overall volume of the 4 CSTRs corresponds to a tau k of 9, so maybe each one is 9 over 4, whatever it is. And basically this will achieve a much higher conversion compared to just having one much bigger CSTR, okay? Even though it's still less efficient than a single PFR, however, it's much better than using a much larger CSTR. So these are just basically the conclusions you need to know from these slides, is that for nth order reactions and any duty, the volume of the CSTR is always bigger than the volume of the PFR. So you need to know this. The ratio of the volume of the CSTR to that of the PFR increases as the reaction order increases. So also be aware of this. So as the reaction order increases, the ratio of volumes, I will need a larger CSTR to achieve the same performance as a PFR. When conversion is small, then the performance is only affected for a small extent by the type of flow. So again, for smaller conversions, both reactors start behaving very similarly. And this, you can see this in this chart, basically, where, at high conversions, the ratio of volumes is much larger, or is very high compared to at low conversions, where you can see the ratio of volumes is very low. Even, if you want conversion of 0, you don't want any conversion, or you want conversion of 0.01, a very low conversion, then, you can, the CSTR and the PFR, having a CSTR and a PFR with the same volumes will give you this very same low conversion. However, if you're targeting a much higher conversion, or if you're targeting an intermediate conversion, you can see that you'll need a much larger CSTR to achieve this conversion compared to a PFR. Okay? And this here, these conclusions are all shown here. When the conversion is high, then the performance is strongly affected by a type of flow. So this is what we just said. If you're designing a reactor with high conversion, you must describe the mixing very well. And this is a very important point. And then fractional changes in volume on reaction change the volume of the CSTR to PFR, but to a relatively minor extent. Okay. So basically what this means is that epsilon has minimum effect on the ratio of CSTR to PFR. So if you look here at this slide up here, you can see for a first order reaction, n equals 0, when epsilon equals 0 is the dashed solid line, epsilon equals 1 is the solid line, epsilon equals 1 is this dotted line, epsilon equals 2 is this dotted line, and the difference between, epsilon equals 2, epsilon equals 0 is not that large, really. Epsilon does not have a large effect. You're not seeing any different trend. It's just, within the margin of error. And then an additional conclusion you need to know is that it's always better to number up the CSTRs than to use a larger CSTR, okay? And by this, I mean, one second. You can, if you want to if you want to achieve a very high conversion using a CSTR, instead of using one CSTR with a much larger volume, or even two CSTRs with a much larger volume, you can number up the CSTRs. So basically break up your CSTR into a bunch of smaller CSTRs with the same equivalent overall volume, and you can achieve the same conversion. Okay, so let's say I want to achieve a conversion of 0.98, so I want to reach this line right here, and I want to achieve this line right here, and my original CSTR is, my original CSTR has a volume of, let's say 5, maybe not use 20, let's say 5. So this is my original CSTR, has an original volume or a tau k of 5. So if I want to achieve this high conversion, I can either increase the volume, so I can increase the volume from 5, I can increase the volume from here all the way to here, and you can see this is almost a 10-fold increase in volume, right? So if my volume here is 5 meter cubed, I need to get 50 meter cubed reactor just to achieve this conversion. So this is just using a larger CSTR. Alternatively, I can just number up the CSTRs. So instead of using one CSTR, I can 2, 3, 4, maybe even here 4.5, 5 CSTRs. So if I use 5 CSTRs with the same overall volume, I can still achieve this conversion. So instead of using a much larger CSTR, I'm going to just use 5 smaller CSTRs with the same overall volume. Same overall volume. So basically I have a large CSTR. I mean, theoretically or mathematically, you're breaking it down into 5 smaller CSTRs. Practically, you're buying 5 smaller vessels. Just be careful about, just for, so that you're aware, sorry. And if I basically break it down into 5 smaller CSTRs with the same equivalent volume, or if I buy 5 smaller vessels with the same equivalent volume, I can achieve this very high conversion without really having to use a massive CSTR, right? And this is usually better. Economically, this is cheaper, because safety-wise, you have the hazards are much lower. From an operational perspective, the operational costs are much lower. From a mixing perspective, the mixing is much simpler. You can control it better from a control perspective, much easier to control. So the idea of numbering up is always better than using a larger CSTR. Okay, let's move on from this, and you can always rewatch the previous lectures or read the slides or read your book, whichever works for you. Just be aware of these concepts. Okay. The next concept we need to be aware of is having equal size CSTRs in series. And you must know that as n becomes large, n CSTRs behave as one PFR, right? So if I have an infinite number of CSTRs in series, they behave exactly like a PFR. And as the number of CSTRs in series increases, the performance gets much closer to that of a single PFR. And you also need to be aware of these equations and how to manipulate them. Specifically, CA note over CA final is equal to 1 plus K tau I to the power n. You need to know this. And again, tau I is equal to tau total divided by n. So if I tell you, the overall residence time in 5 CSTRs is 1. So the residence time in each CSTR is 1 over 5. And this equation basically describes the behavior in n CSTRs, okay? And the typical type of problem will give you n CSTRs and asks you to compare it to a single PFR. So in order to do this for a first order reaction, we'll be dealing with first order reactions for this type of problem. You're basically comparing this equation right here, which is CA naught over CAF is equal to 1 plus K tau I to the n, to this equation right here, which is CAF over CA naught is equal to exponential of minus K tau, right? So this versus CA naught over CAF, 1 plus K tau to the n. K tau I to the power n, and the typical problem will involve you using these two equations together. Maybe use this one to get the K, then plug the K here to get the tau, or get the CA naught, whatever it is. Just using these two equations not interchangeably, in a supplementary fashion. Okay. And then these two slides might show up in the multiple choice portion. You're not gonna get problems to solve, but it's good to know them, that if I have plug flow reactors in series, they behave like one larger PFR, right? So if I have 2 plug flow reactors in series, this is 0.5, this is 0.5, they behave the same as one large PFR, the volume of 1, right? Whereas if you have plug flow reactors in parallel, to optimize the performance, you need to make sure that the space-time tau 1 and tau 2 are the same, right? If tau 1 is equal to tau 2, this means that you have the optimum performance. If tau 1 is much larger than tau 2, then your performance is suboptimal when you have plug flow reactors in parallel. The recycle reactor, you also need to know, it's important to know the definition of a recycle, or the idea of a recycle. I'm sure you're all familiar with it, but keep it in mind, because in almost any type of in many operations, actually, you will have a recycle, especially in operations where you have a chemical which is very valuable, or a chemical which is very dangerous, you don't want to get rid of. All of this stuff, you tend to have a recycle. And as we said before, R is basically the volume returned divided by the volume leaving. So it's this branch divided by this branch, right? You should also be aware that some books define it differently. So some books define it as this branch divided by this branch. Some books divide it as this branch this branch, whatever it is, just be aware of this recycle ratio. In our course, we're using volume returned over volume leaving. Okay, and this is the performance equation for a recycle reactor. There's a homework and there's a problem in homework number 4 about this. Just go over it, read it. It might show up, it might not. But it's very simple, really. It's just the same equation as a PFR. Performance equation, I just have R plus 1, and I have R and R here. So if I tell you R is 2, just have a constant here, and then you have your limit changes here. It's very simple mathematically. So please just revise it and be comfortable with it. And final thing about the PFR, so this might show up on your multiple choice, where as the recycle approaches infinity, your reactor behaves like a CSTR. As the recycle approaches 0, your reactor behaves as a PFR, right? So if you think about it, this is my PFR with a recycle. If the recycle is 0, then it's just basically a PFR. If the recycle is infinity, it's a CSTR, right? It's just mixing all the time, and it's basically a CSTR. So just be aware of this as well. And yeah, this is the end of it, of what you really need to focus on as you prepare for your test. Please prepare in advance for your test. I will, office hours will be on Thursday. Please use them as needed. Send me an email anytime if you have any questions. We can schedule a time to talk even on Saturday if you want. If you really want to study, or on Sunday if you really want to, if you have any questions and you want to ask me, just send me an email. I'll also try to have office hours on Monday to be available if anyone has any questions. Thank you very much. A second video about the homework is very important, so please listen to that one as well. Thank you.